Lorentz factor. In this video we'll go through the Lorentz factor. There's a lot of dot points to cover in the SACE guideline, however really it's just one equation. To set this up, we'll start with a few definitions. So proper time is a time interval between two events that are measured in the reference frame which is at rest. Time dilation refers to the slowing down of clocks that are in motion relative to an observer. Okay, so when we watched that Maxwell's Demon video, we saw that when we were moving, the clocks that we were looking at slowed down. Now we can actually calculate the dilation of time using Lorentz formula. Have a look for this one on your formula sheet. The time observed is multiplied by gamma, which is the Lorentz factor, to determine the time of the event in the moving reference frame. So the Lorentz factor is a ratio that indicates a factor by which the time, the length, or the mass is changed in a moving reference frame. And you can see in the formula itself, it compares the moving reference frame's velocity to that of the speed of light. So we've mentioned proper time, now let's look at proper length. So the proper length of an object is the length recorded in a reference frame where the object is at rest. And the length contraction refers to the decrease in length of an object that is in motion relative to the observer. This suggests when we're standing still and looking at an object that's approaching the speed of light, it actually appears shorter than its actual length. As part of the Year 11 course, we looked at half-life of radioactive substances, which is the time it takes for half the particles of a substance to decay. Now, when we're looking at these particles in a different reference frame, the half-life of these particles are actually different, and this is due to the effect of time dilation. So an example is muons. They're unstable subatomic particles that are created when cosmic rays hit our atmosphere. At rest, the half-life of a muon is 2.2 microseconds, and the speed that they're traveling at when they're created is 99.8% the speed of light. So using classical physics, we can calculate the distance that they travel in this scenario. Okay, so we can see the formula on our screen, and it travels 659 meters in this classical physics. Classical physics tells us that the particles will travel 659 meters. However, what we can do is actually detect them on the surface of the Earth, which is over 5,000 meters further than the classical physics suggests. So the life of the muons is actually extended in the reference frame of the Earth, as the muons are moving at a very high speed relative to the Earth. So what we can do is we can use Lorentz factor to actually determine the half-life of one of these muons traveling at that speed. So previously it was 2.2 microseconds, but what we can see is that due to the relativistic effects, from our observer's point of view, the time dilation gives the half-life of the muon as 34.8 microseconds. So given the extended half-life of the muon, you can see that using that same formula for motion that we had before, instead of the 2.2 microseconds, we're going to use the new 34.8, and the muon actually travels a greater distance. And that's why we can detect a greater number of muons on the surface of the Earth. As with time and length, the mass of an object can change at high speeds approaching the speed of light, and in turn, the momentum of an object. This is shown by the formula on the screen. So observing this formula a little further, we can see that as the speed of the object gets faster and faster, it can approach the speed of light, leading this term toward the value of 1. And then doing the calculation, 1 take a number that's close to 1 is going to result in a number that's approaching 0, suggesting that the Lorentz factor will be very, very large. However, if the speed was actually equal to the speed of light, then this denominator will be 0, and the relative mass tend towards infinity, which isn't possible. So this means that nothing can travel at the speed of light. Explain why some particles that are created in the atmosphere of Earth that also have very short half-lives are able to be detected on the surface of the Earth.